Good morning, everyone, and a pleasant morning to all the students. Once again, a happy welcome for the chemistry webinar. Myself, Mrs. Sridevi Polu, Principal, TSMS Pudu, is privileged to be here and to introduce you the speaker of the day, Mr. Jahangir Garu, PGT Chemistry from TSMS Banfaram from Vikarabad district. Dear children, in our previous sessions, we have learnt about states of matter, gas laws, kinetic molecular theory of gases and its postulates, and how all these gas laws are deduced from kinetic gas equation. And today, dear children, it's the last session in states of matter. See, today we are going to conclude this chapter, and then whatever the topics which are left over will be completed by Jahangir sir. And here I want to mention you one thing, children. So in our previous sessions, we have learned about 4 chapters, isn't it? See, atomic structure, periodic classification of elements, chemical bonding, and then today it is the states of matter. See, I hope everyone has wrote the notes of these chapters and you are preparing for your examinations. Okay, so please keep this in your mind and then let's ready for the class. So good morning, Jahangir sir.
Good morning, madam.
Good morning, sir.
Good
so
morning.
Today, what topics you are going to deal, sir?
So today we are going to discuss deduction of kinetic energy from kinetic gas equation.
Yes, sir.
The next one is a deviation of deviation of ideal gases from real gas behavior.
Okay.
The next one is a liquefaction of gases and liquid state and some of the physical properties of liquids.
So, okay, I think you are ready with the important questions.
Yes,
which
yes.
are
At the end,
for IP from this chapter,
yes,
isn't it?
yes, madam. At the end of the session, I'm going to give most important questions in this chapter, which will come in the final examination. 99% is maximum.
Okay. Okay, children. So please note down all the questions which will appear from this chapter for your IPE. See, I hope everyone is ready for the class. Okay. So thank you, Jahangir sir.
Thank you, madam. Good morning, respected principals and teachers. And good morning, students. So today we are going to discuss last topics in this lesson, states of matter. So before the discussing of the topics in this last session, once we recap what we were discussed in the previous sessions. So the first topic is kinetic molecular theory of gases and kinetic gas equation, deduction of all gas laws like Boyle's law, Charles' law, Avogadro's laws, Dalton's laws, and Graham's law of diffusion from kinetic gas equation, and types of molecular speeds we were discussed in the previous session. Okay, now come to the today's session. We will cover these topics. So before going to detailed study of these topics, once we look at the glance of side headings of these sessions, first one is deduction of kinetic energy equation from kinetic gas equation, behavior of real gases and deviation from ideal gas behavior, liquefaction of gases, and next liquid state and physical properties of liquid state. Under the physical properties of liquid states, we will discuss some of the physical properties: vapor pressure, surface tension, and viscosity. So these are the subtopics we are going to discuss in this session, students. Okay, so now come to the first subtopics is kinetic energy of gas, deduction of kinetic energy of gas from kinetic gas equation. So students, what is kinetic gas equation? Kinetic gas equation we discussed in the last session. The formula or the equation of kinetic gas equation is PV is equal to 1 upon 3 mn u square. It is kinetic gas equation. So PV is equal to 1 upon 3 mn u square is kinetic gas equation. So now next step is PV is equal to 1 upon 3 small m and lowercase n and lowercase of m multiplied, you will get capital M. That means n number of molecules are there and their molecular mass is m. By multiplying of these two, that gives you overall molecular mass of the gases. How many molecules are there? That molecules total molecular mass is represented with capital M. So 1 by 3 mu square. Then the next step, divide and multiplied with 2. So we are dividing and multiplying with the same number. Hence there is no change in equation. Hence here we are dividing and multiplying with a 2. So 2 by 3 of 1 by 2 mu square. So already we know that the kinetic energy formula Ek is equal to half mu square. You also learned in the physics kinetic energy of a equation or kinetic energy formula of mv square. Potential energy, kinetic energy you learned in physics also. So here kinetic energy Ek is equal to half mu square. Now I am replacing in place of half mu square or 1 upon 2 of mu square with Ek. So then equation becomes PV is equal to 2 upon 3 of Ek. But according to the kinetic, according to the ideal gas equation, what is the ideal gas equation? PV is equal to nRT. For 1 mole of gas, PV is equal to becomes RT. Then now replace PV with by RT. Then RT is equal to 2 by 3 of Ek. So from this, by making of subject Ek is equal to transposition of 2 by 3 to the opposite side, it becomes 3 by 2. So 3 by 2 RT for 1 mole of gas. If it is for n mole of gas, Ek is equal to 3 by 2 nRT. So 3 constant, 2 constant, and n means number of moles. It depends upon the gas. That is also constant. R is universal gas constant. And T is what? Absolute temperature. So from this we can say that anyway 3 by 2 constant, n constant, and R constant. So means the kinetic energy is related to the temperature. Means kinetic energy of gas is directly proportional to the absolute temperature. So this is the deduction. We derived the deductions from kinetic gas equation. Next one, if it is a kinetic energy of energy is applicable for 1 molecule of gas, n means what? Number of molecules. Then it is becomes Ek by n. Ek upon n is equal to 3 by 2 of R by n into T. So here R is nothing but universal gas constant. N means what? Number of molecules or Avogadro numbers. R by n is equal to, consider as another constant K. So here K is called as Boltzman constant. K is called as what? Boltzman constant. And its value is 1.38 into 10 to the power of minus 16. Or Kelvin inverse, molecule inverse, or 1.38 into 10 to the power of minus 23 joule Kelvin inverse, molecule inverse. This is very, very important in 2 marks point of view. What is Boltzmann constant and give its value? It is very important. What is Boltzmann constant? Give its value. What is the Boltzmann constant? Boltzmann constant is nothing but universal gas constant per number of molecules. Universal gas constant per number of molecule is known as what? Boltzmann constant, and its values are 1.38 into 10 to the power of minus 16 air Kelvin inverse, molecule inverse. And similarly 1.38 into 10 to the power of minus 23 joule Kelvin inverse, molecule inverse. So this is very important. So that is Boltzmann constant. So based on this kinetic energy, we'll do one problem. So numerical problem, it is also most important in 2 marks point of view. So calculate the kinetic energy of 5 moles of nitrogen at 27 degrees Celsius. Calculate the kinetic energy of 5 moles. How many moles? 5 moles of nitrogen. At what temperature, student? 27 degrees centigrade temperature. So come to the solution of this problem is, kinetic energy. Just now we derived the kinetic energy formula. Kinetic energy of gas is equal to 3 upon 2 nRT. N means what, student? Number of moles. R means what? Universal gas constant. T means absolute temperature. N, how many moles given in the problem? 5 moles. R is equal to universal gas constant. Its value is taken as 8.314. Anyway, it is constant. 8.314 joule mole inverse Kelvin inverse. T means what? Absolute temperature. Absolute temperatures are always measured in Kelvin scale. Hence why conversion of degree Celsius into Kelvin scale, so just you add 273. So 27 degrees Celsius plus 273, that gives you 300 kelvins. Now substitute these all values in the kinetic energy equation formula. So come to the kinetic energy equation. Ek is equal to 3 upon 2 into N. N is 5 number of moles. R is universal gas constant. Its value 8.314 into T. T means what? Temperature 300. So by simplification of these values, you will get 18,706.50 joules. So this is one of the most important expected question in IP examination point of view. Calculate the kinetic energy of 5 moles of nitrogen at 27 degrees. Not only this, here concept is very important. Some numericals or some information or data will be changed, but concept is very, very important. So this is one of the numerical problem based on kinetic energy. So next come to student. Yeah, behavior of real gases and deviation from ideal gas behavior. So in previous session, we were discussed what is mean by ideal gases. Ideal gas means what? Ideal gases are nothing but gases which follows all gas laws. Like Boyle's law, Charles' law, and Avogadro's laws is known as what? Ideal gases. They are called as what? Ideal gases. So all gas laws, whatever the gas laws we discussed, those gas laws are completely or strictly obeys. Such gases are known as what? Ideal gases. So in our universe, there is no ideal gases or there is no perfect gases. Ideal gases also named as perfect gases. But in our universe, whatever the gases are there, they are comes under of real gases only. So ideal gases is a hypothetical phenomena or hypothetical gases. But in come to the nature, whatever the gases are surrounded around us, they are called as what? Real gases. What is mean by real gases? Real gases are nothing but a real gas, one which actually exists, whether it is obeys gas laws strictly or not. They may follow the gas laws strictly or not. Means they may follow or may not follow. Such gases are known as what? Real gases. So like ideal gases and real gases. The difference between the ideal gases and real gases. Ideal gas means completely and strictly follow the gas laws is ideal gases. Real gas means they may obey or may not obey the gas laws is called as real gases. So what is the reason for the deviation of the real gases from ideal gas nature or ideal gases behavior? We'll discuss in the next continuation. So to measure the deviation of the real gases from ideal gases behavior, we have one method that is known as what? Compressibility factor. So one of the convenient method for to study the nature of ideal gases, real gases from the ideal gases behavior is what? Compressibility factor. A very convenient method for studying the deviation of real gases from ideal behavior is through a compressibility factor. The compressibility factor is denoted, represented with Z. Z is equal to PV upon nRT. So with the help of compressibility factor, we will study deviation from real gases to ideal gases. How they are deviating from the nature of real gases to the ideal gases. So this compressibility factor Z also can be expressed as a ratio of real volumes to the ideal volume. Real volumes to the ideal volume. So the formula of compressibility factor is Z is equal to PV upon nRT, or Z is equal to volume of the real gases to the volume of the ideal gases. So in case of ideal gases, if you take the ideal gases, for ideal gases Z is equal to 1 always. For real in ideal gases, what is the value of compressibility factor, students? compressibility factor value Z always is equal to 1. If Z is equal to 1, then what is the equation now is become PV is equal to nRT, because if you substitute in place of Z by 1, then the equation is becomes what? PV is equal to nRT. PV is equal to nRT is nothing but it's a ideal gas equation. But come to the real gases, Z not equal to 1. Z not equal to 1. Z not equals 1 means PV is also not equal to nRT. PV is also not equal to 1RT. So Z not equal to 1 means what? Z may be greater than 1 or maybe less than 1, but not is equal to 1. That means, so if in case of the compressibility factor Z is greater than 1, that means what? The gas shows positive deviation from ideal behavior. They shows what? Positive deviation from the ideal behavior. That means what? Such gases are less compressible. Such gases are what? Less compressible. And if in case of Z is less than 1, the gases are shows what? Negative deviation from the ideal behavior, and they are what? More compressible. So the deviation of the real gases from ideal behavior we can clearly explained with the help of 1. When Z, how when Z greater than 1 and Z less than 1, here one graph is there. See children, students, so here on y-axis compressibility factor is taken, Z is equal to, so Z is equal to PV upon nRT, it is taken an y-axis. On x-axis pressure is taken. So if your graph is plotted between these two factors, so for different gases different curves are obtained here. Different gases for different curves are obtained. So here one of the parallel axis, parallel line is there, which is parallel to the x-axis. That is what? Ideal gas line or ideal gas line. So with respect to ideal gas lines, we will observe the remaining gases nature. So here some of the gases are, or some of the gas curves are below this ideal gas curve. Below this ideal gas for initially means oxygen, methane, carbon dioxide are below this ideal gas line. Means below this ideal gas line means Z value is less than 1. That means that's why here Z value is 0.8 or 0.6 or 0.4, means their values are less than 1. In the here some of the gas rays are obtained above the ideal gas line or above the ideal gas line. So what are the gases? Like nitrogen gases, hydrogen gases, oxygen gases, especially hydrogen gas here. Hydrogen and nitrogen gases are above the ideal gas line, means these gases value compressibility factor is greater than 1. These are values are greater than 1 and these gases values are less than 1. So like some of the gases are showing positive deviation. Positive deviation means above this ideal gas line. Negative deviation means below this ideal gas line. So positive deviation showing and some of the gases are showing negative deviation. So it can be represented graphically with the help of compressibility factor. Next one is, here one more graph is there between the pressure and volume. So students, we were discussed in the Boyle's law, the graph is plotted between the pressure versus volume at constant temperature. They are called as isotherms. Here also the two curves are drawn. One is real gas curve and other one is ideal gas curve. One is ideal gas curve and the other one is real gas curve. So here real gases are showing more volume. Why we got the real gas volume above means real gases are volume is more. If you draw a line, here, the volume of real gases is more than that of the volume of the ideal gases. This is the volume of the ideal gases and this one is the volume of the real gases. So real gases are volume is more, means at a high pressure real gases volume is more and comparatively ideal gases when the pressure is decreases, here ideal gases curve is merges to the real gases curves. Means at low pressure, what is the meaning of this one? Merging of these two lines are occurs at low pressure. This is what? Low pressure. So at low pressure, real gases are behaving like a ideal gases nature or ideal gases behavior. So this is the meaning of a graph. Next one is So what is the reason for the deviation of the real gases from the ideal gas behavior explained by the scientist Van der Waals with his Van der Waals equation. So the main reason for the deviation of the real gases from the ideal behavior due to there are two faulty assumptions in the kinetic molecular theory of the gases. We will discuss the postulates of kinetic molecular theory of the gases, like gases contains large number of discrete particles. They are called as molecules. They collide with each other as well also collide with the walls of the container. The volume occupied by the gas molecule is negligible. Like several postulates we were discussed in the previous session. So in those postulates, the two postulates are causes for the deviation of the real gases from ideal gas behavior. So what are those two postulates? Means the first postulate is the actual volume of the gas molecule is negligible compared to the total volume of the container. Actual volume of the gas molecule is negligible comparatively total volume of the container. So for example, this is a container. In this container, gas molecules are present. According to the gas molecules ideal gas nature, so the volume of this gas molecule is very small. That's why according to the kinetic molecular theory of the gases, this volume can be neglected. According to the kinetic molecular theory of the gases, the space occupied by the gas molecule is negligible comparatively total volume of the container. But this is not possible in case of real gases. Even small volume of the gases also can be taken into the consideration for real gases. This is the one of the faulty assumptions according to the kinetic molecular theory of the gases. Okay, so this is the first one of the fault. Next one is what is the second one? Intermolecular force of attractions are not present in gases. According to the ideal gas equations, there is no attractive forces or there is no repulsive forces between the gas molecules according to the ideal gases. But come to the real gases, in the real gases there exist attractive forces as well also repulsive forces are present. So that's why these are the two faulty assumptions. One is the volume is neglected comparatively total volume of the container. This is one of the faulty assumption. And second one is there is no attractive and repulsive forces are present between the gas molecules. There is no attractive and repulsive forces are present between the gas molecules. So that is also one of the faulty assumptions under the kinetic molecular theory of the gases. So these faulty assumptions are corrected by the Van der Waals equations. That Van der Waals equation is applicable for both real gases and as well also ideal gases. That's why he made two corrections. So what are the two corrections here? So Van der Waals pointed out that in the case of real gases, molecules do have a volume and also exerts intermolecular attractions, especially when the pressure is high and the temperature is low. Okay. So he applied the two corrections. One of the correction is volume corrections. Volume correction. So actually what is the corrected volume? Vi means ideal gas volume is equal to V total volume minus B. B is a constant which is for 1 mole of gas, and Vi is equal to Vb minus Nb for n moles of gas. Here B is called as a co-volume or excluded volume because they are not included in the real gas. So co-volume are also called excluded volume, which is constant for each gas. Yes. Again, take a gas molecules container. Here, this is the volume occupied by the gas molecules. According to this kinetic molecular theory of the gases, this volume is neglected. This volume is what? Neglected. But come to the real gases, this volume also taken into the consideration. So means, so Vi means ideal gas behavior. Vi is equal to real gases. When we'll get ideal gas volume? Ideal gas volume is this volume is only ideal gas volume. That's why this volume is subtracted. That means Vi is equal to V. V means what? Total volume of this container minus to the N into B. N means number of moles. B means what? Excluded volume. This volume is called excluded volume or also called as a co-volume. Excluded volume are also called covolume. So by subtraction from the total volume, of the container, we will get the ideal gas volume Vi. So this is for correction of the volume correction. Vi is equal to V minus Nb for n moles of gas. Okay. So the excluded volume B is actually 4 times the actual volume of the gas molecule. It is how many times? 4 times that of the actual volume of the gas. So the next one is pressure correction. So pressure correction is nothing but a P ideal is equal to P observed plus P dash. P dash is what here? Pressure correction. So usually here pressure is depends upon the two factor. According to the ideal gases, there is no attractive forces and repulsive forces. But come to the real gases, there is attractive forces and as well as repulsive forces. So here pressure is depends upon the two factors. One is the molecules which are present in the walls of the container are the colliding with the walls of the container, and the second one is inside of the or middle of the gas molecules. Here the attractive force exerted on a single molecule about to strike the wall is proportional to the number of molecules per unit volume in the bulk of the gas. This is a one attractive force is developed. The second attractive force is the number of molecules striking the walls, which is also proportional to the number of molecules present per unit volume of the gas. Means here pressure is exerting two types. One is the molecules which are colliding with the walls of the container also exerts pressure, and the second one is pressure exerted by the molecules which are inside of the gas molecule. They pull the walls of the container gas molecules. They pulling the walls of the container of the gas molecules. Means there are two types of pressures: pressure exerted by the walls of the container of the molecules and also pressure exerted by the interior of the gas molecules. That's why the pressure of the gas molecule is directly proportional to this density of the gas. Hence why the attractive force is directly proportional to the square of the density of the gases. Hence P dash is directly proportional to the total attractive force, means walls of the container attractive force as well also inside of the molecules of the attractive force. So P dash is directly proportional to the density of the gas. Density is nothing but mass by volume, but mass is anyway constant, same for total number of molecules which are present in the gas of the container. That's why P dash is directly proportional to 1 upon V square. By removing this proportionality, we'll get constant, that is A by V square. So from that we can idea P ideal is equal to P observed plus P dash. P observed plus P dash. So P ideal is equal to P observed plus P dash we got is A by V square. Now substitute this pressure correction and as well also volume correction in the ideal gas equation. What is the ideal gas equation? PV is equal to nRT for 1 mole of gas. So P pressure. So here corrected value is P ideal is equal to P observed plus A by V square. P plus A by V square. Next volume correction is V minus B is equal to RT for 1 mole of gas. For n mole of gas, P plus A n square by V square. V minus NB is equal to nRT for n moles of gas. This is the van der Waals equation which is applicable for real gases and as well also ideal gases also. This is a van der Waals equation derivation. Van der Waals equation P plus A n square by V square, V minus NB is equal to nRT. Okay. So the next one is Boyle's temperature. What is meant by Boyle's temperature? Means the temperature at which real gases are obeys ideal gas. The temperature at which real gases are obeys what? Ideal gas laws over an appreciable range of pressure is called as what? Boyle's temperature. So means real gases also behave like a ideal gases at low pressure and high temperatures. So at particular temperatures, real gases also behaving like a ideal gases. Previously one graph I show you, real gases curve and ideal gases curves are merged. Real gases curve and ideal gas curve is merged at low pressure, as well also temperature is also important at that particular temperature. So that temperature is known as what? Boyle's temperature. What is called? Boyle's temperature. So after this, next to come to the next one is liquefaction of gases. Liquefaction of gases. What is mean by liquefaction of gases? Means conversion of a gaseous state of matter into the liquid is generally called as liquefaction. Students, for a conversion of any physical state of matter from one physical state to another physical states, there are two important factors are plays important role. One is called as the temperature and other one is pressure. So for liquefaction of gases, first studied by scientist Andrews, the essential condition for liquefaction of gases were discovered by Andrews as a result of his study of pressure, volume, temperature relationship for carbon dioxide gas especially. Okay. So what are the conditions are required for liquefaction of gases? One is temperature and other one is what? Pressure. These are the two important factors for liquefaction of gases. By decreasing of temperature and other one is increasing of pressure, we can convert the gaseous state of matter into the liquid state. Okay. So while converting of any gaseous state of matter into the liquid state of matter, there are some critical constants are plays very important role. So for conversion of gaseous state of matter into the liquid state, for every gas there is a particular temperature is should be reached. Then only it is converted into the gaseous state. Means alone by applying of pressure we cannot convert. Only by applying of pressure we cannot convert gas into liquid. Temperature is also plays a very important role in the conversion of gases to the liquid. So the temperature is called as what? Critical temperature. What is meant by critical temperature? Means the temperature below which gas can be liquefied by the application of pressure alone is called as critical temperature. Means whenever the gas is reached to the particular temperature, then only it starts converting into gaseous state to liquid state. Here, simple example, carbon dioxide gas. The carbon dioxide gas critical temperature is 30.98 degrees Celsius. That means whenever the carbon dioxide gas is reaches to the temperature of 30.98 degrees Celsius, then only the carbon dioxide gas is converted into the liquid state. Otherwise, above this temperature, how much pressure is applied, then it is not possible to convert from a gaseous state to liquid state. So this particular temperature is called as what? Critical temperature. Like for every gas, there is a particular temperature. Then only if for every gas, there is a particular temperature. When it is reaches to the particular temperature, then they starts converting from gas to liquid. So this is in case of carbon dioxide gas. So that is called as what? Critical temperature. So second one is critical pressure. The pressure required to liquefy a gas at critical temperature is called as critical pressure. Simultaneously, pressure is also plays very important role. The pressure is also required to liquefy a gas at a critical temperature is called as critical pressure. Example, carbon dioxide gas. The carbon dioxide gas critical pressure is 73 atmospheric pressure. 73 atmospheric pressure. So like carbon dioxide gas when reaches to the 30.98 degrees Celsius temperature, at the time that pressure is 73, then it starts converting from gaseous state to liquid state. Above this temperature means 31 degrees, 32 degrees, 35 degrees, 50 degrees. Above this temperature, how much if you pressure is applied, then it is not possible to convert from gaseous state to liquid state. When carbon dioxide reaches to this particular temperature, then only it starts converts from gaseous state to liquid state. That is called critical temperature and critical pressure. And last, critical volume. Critical volume is nothing but the volume occupied by 1 mole of a substance at critical temperature and pressure is called as critical volume. So example, again same carbon dioxide gas, the critical volume is 94.12 meter cube per kg. So like for conversion of or liquefaction of any gas, these critical constants are plays very important role. Whenever the gases are reaches to the particular critical constant, then only they starts from gaseous state to liquid state. So that's why these are the critical constant should be reached by gas, then only they convert from gaseous state to liquid state. So here Sir Andrews explained the isotherms of carbon dioxide gas at various temperatures. So in according to the Boyle's law, we learned that if graph is plotted between the pressure versus volume at constant temperature is called as what? Isotherms. So here isotherms of carbon dioxide gas at various temperatures are mentioned. According to the Andrews studies, So here at a different temperature, different curves are obtained here. Students, here different temperature, different curves are obtained at 50 degrees Celsius temperature, 31.1 degrees Celsius temperature, 30.98 degrees Celsius temperature, and next one is a 21.5 degrees Celsius temperature and 13.1 degrees Celsius temperature. So like at a different temperatures, he was studied the isotherms of these carbon dioxide gases at various temperature. If you observe first at 50 degrees Celsius temperature, at 50 degrees Celsius temperature, here the graph shows pressure versus volume. Here volume is decreases and pressure is increasing. Volume is decreasing and pressure is increasing. How much pressure is applied? It is present in gaseous state only. It is present in what? Gaseous state only. Means similarly, means it whenever it is reaches to the particular temperature, then only it starts converting into the liquid state. So 50 degrees temperature is not sufficient for conversion of carbon dioxide gas into liquid. This is an indication of this curve. And the second one is 31.1 degrees Celsius temperature, one curve is done. Here also volume is decreasing and pressure is increasing, even though it is not converted into the liquid state. How much your pressure is applied? Means alone pressure is not sufficient for conversion of gaseous state of matter into the liquid state. That is the one what I want to say here. Alone pressure cannot sufficient for conversion of gaseous state of matter into the liquid state. And next one is another curve here, blue line. What is the temperature? 30.98 degrees Celsius temperature. So as well as volume is decreases and pressure is increases whenever it is reaches to the particular point. This is red dot ball point indicates a particular point. What is the temperature here? 30.98 degrees Celsius temperature, and its pressure is how much? 73 atmospheric pressure. So whenever the carbon dioxide gases reaches to this particular point, what is the temperature? 30.9 degrees Celsius and the pressure is 73. Then it starts converting from initially starting point here. It starts converting from a gaseous carbon dioxide into the liquid carbon dioxide. So this point is known as critical constant values, and this temperature is called as critical temperature, and its pressure is called as a critical pressure. Means whenever the carbon dioxide gases reaches to this particular temperature, this is exclusively for carbon dioxide. It is not common or same for remaining gases. It is depending upon the nature of the gas. This is only for carbon dioxide gas. So whenever the carbon dioxide gases reaches to the temperature of 30.98 degrees Celsius and its atmospheric pressure is 73, then carbon dioxide gas is converted into the liquid state. Now, as the temperature is decreasing here, like 21.5 degrees Celsius temperature, you can see the curve from A to B here. The temperature volume is decreases and the pressure is increases. Whenever it is reaches to the point B, it starts converting from a gaseous carbon dioxide into the liquid carbon dioxide. So suddenly and rapidly, the volume is decreases from B to C. So here in between the B to C, the gaseous carbon dioxide and the liquid carbon dioxide are exist in a equilibrium. So whenever it is reaches to the point C, the liquefaction is completed. Means the gaseous carbon dioxide is completely converted into the liquid state. So after that, how much pressure applied, we cannot compress, because we know that one of the property of liquid is liquids we cannot compress. Liquids we cannot compress. Okay. So similarly, another graph is this is also 31 degrees Celsius temperature. Also here, volume is decreases and pressure is increases, and this is a horizontal line which is parallel to x-axis is a equilibrium state of gas and liquids. At the end point is represents a what? Completion of gaseous state of matter into the liquid state. Okay, so at this point the liquefaction part is completed, means completely converted into this liquid state. And this cone shows that existence of liquid state of matter and gaseous state in equilibrium. This is a equilibrium state of liquid state and gaseous state, means gaseous state is gradually converting into the liquid state. Okay, so next one is come to the up to now we discussed about the gaseous states of matter and characteristics of gaseous state of matters and interconversion of matter and van der Waals equation, and come to the second physical state of matter is liquid state. So generally, you know very well about this. In the lower section also studied some of the characteristics of liquid state. Just once we go through these characteristics of liquid states. So liquids have no fixed shape but has fixed volumes. So there is no particular shape for liquids but have the particular volume. And intermolecular forces are intermediate between the solids and liquids. Means neither very strong, neither very weak. Means neither very strong nor very weak. So solids are high intermolecular force of attraction, gases are very low intermolecular force action, but it is intermediate between the solids and gases. And third one is intermolecular space also between the solids and liquids. Intermolecular space is also between the solids and liquids. Molecules of the liquids can be move fast from one another freely. Therefore, liquids also called as what? Fluids. And the liquids are denser than that of gases. Liquids are denser than that of gases. Now come to the some of the physical properties of the liquids are one of the physical properties is vapor pressure. What is mean by vapor pressure, students? Vapor pressure is nothing but the pressure exerted by the vapor molecules on the surface of the liquid when the rate of condensation becomes equal to rate of evaporation is called as vapor pressure. Vapor pressure. Example, so if it is a liquid is taken, so this is a liquid and this liquid is present in a closed container. Generally, liquid molecules are converting into the vapor. Liquid molecules are converting into the vapor at any temperature. That is called as what? Evaporation. This evaporated molecules are again becomes what? Condensed. Means liquid molecules are converting into the vapor and parallelly vapor molecules are converting into the liquids. So the number of liquid molecules are converting into the vapor molecules are converting into the liquid at one of the particular time, that becomes what? Equal. Example means if 10 liquid molecules are converting into the vapor, the same 10 vapor molecules are converting into the liquids. That is called as rate of evaporation. Rate of evaporation means liquid is converted into the vapor. That is rate of evaporation. Rate of condensation means vapor molecules are converting into the again what? Liquids is called rate of condensation. So at one particular point, evaporated molecules are becomes equal to the condensation molecules. That pressure in such cases, the pressure is exerted this vapor molecules. The pressure is exerted by this vapor molecule. Such pressure is known as what? Vapor pressure. Vapor pressure. So that is the vapor pressure definition, students. So next one is boiling point. Boiling point means the temperature at which vapor pressure of the liquid becomes equal to atmospheric pressure is known as what? Boiling point. The temperature at which vapor pressure of a liquid becomes equal to the atmospheric pressure. Generally, liquids or vaporize takes place at any temperature, but at one of the particular temperature, the vapor pressure of the liquid is becomes equal to atmospheric pressure. That is called as what? Boiling point. Usually, boiling point of water is 100 degrees Celsius temperature at 1 atmospheric pressure. Means on liquids, vapors also exert pressures. Whenever the temperature is equal to the atmospheric pressure, then liquid starts converting into the gas. That point is known as what? Boiling point. Means when liquid of water is reaches to the 100 degrees Celsius temperature, then it is converted into the gaseous state to the, liquid state to the gaseous state. So that is known as what? Boiling point. So here the different types of curves are given, the boiling points of different types of liquids at different temperatures, like diethyl ether boiling point is 308 kelvins, and carbon tetrachloride is 349.7 kelvins, and 351 ethyl alcohol is 351.3 kelvins, and other one is water is 373 kelvins. Means if it is converted into the degree Celsius, it becomes 100 degrees Celsius. Here values are given in Kelvin scales. So at 1 atmospheric pressure means 760 mm of Hg. At 1 atmospheric pressure, different liquids have different boiling points. So like it is depends upon their intermolecular force of attraction and so many other factors, temperatures and intermolecular force of attractions. Like different liquid state of matter have different boiling points. So these are the curves. And next one is surface tension. Surface tension is nothing but Another liquid state of matter property is surface tension. Surface tension is a measure of this inward force on the surface of the liquid. It acts downwards perpendicular to the plane of the surface. So surface tension is a measure of this inward force on the surface of the liquid. It acts downwards perpendicular to the plane of the surface is called as surface tension. So the surface tension is depends upon the factors like attractive forces between the molecules and temperature. Attractive force is more, surface tension is also more, and the temperature is more, surface tension is becomes less. So it clearly you can understood with the help of this diagram. Here, this is a one liquid. In this liquid, so two types of molecules are present in the environment. One is interior molecules and other one is exterior molecules. Interior molecules, the net force is equal, upward, downward, left and right side. In all the directions, the forces are equal. Hence, the net resultant attractive forces becomes what? Zero. But come to the liquid molecules which are at the surface, here unbalanced forces are present. The balanced forces are acting, unbalanced forces are present. Here the force is acting downward. So the force is acting what? Downward. This downward forces is nothing but a inward force acting the interior of the molecules. So this phenomena is known as what? Surface tension. This concept is called as what? Surface tension. Next one is viscosity. Viscosity is nothing but generally when liquid is dropped on a floor, generally liquid is dropped on a floor, it moves or it fluid certain distance, then after becomes the velocity, the flow of the liquid becomes stops. What is the reason? Because of that phenomena only is called as what? Viscosity. Viscosity is nothing but the property of liquid which determines the resistance. Resistance to flow is called as what? Viscosity. Resistance means what? To become stop. Resistance to flow of liquid is called as what? Viscosity. So this is a picture showing you the explain the viscosity concept, and it is any one of the liquid, whether it is a water or honey or oil or anything. This liquid is consist of a different types of layer, different types of layers. So in these layers, one layer is moving forward and its underneath layer is moving backward. Like this resistance of the flow of liquid is called as what? Viscosity. A regular gradation of velocity in the passing from one layer to the next layer is called as what? Laminar flow. So here the force of attraction between the layer is directly proportional to the area of contact and also directly proportional to the du by dz. It is called as a velocity gradient. Velocity gradient. By combining of these two equations, F is directly proportional to A into du by dz, and removing the proportionality, you will get constant neta n into neta into A into du by dz. N is called as a coefficient of viscosity, and their units are Newton second meter power minus 2 in SI system. Poise also one of the units of system in CGS systems. Okay. So students, what we have learned in the today's session? We learned kinetic energy of gas from kinetic gas equation deductions and deviation from ideal gas behavior and real gases, van der Waals equations, liquefaction of gases and liquid state, and some of the physical properties of liquids we discussed in the today's sessions. So now last and most important one is the most expected important questions in this chapter is actually the weightage of this chapter is 4 marks, means either 4 marks questions or maybe 2 plus 2, means 2 very short questions may come, but maximum 4 marks question only we can expect from by observation of previous question papers. So once you go through this important questions after this session, first question is the most very important one is write the postulates of kinetic molecular theory of the gases. So most very expected and important question, 4 marks. Write any 4 postulates, any 4 minimum, any 4 postulates of the kinetic molecular theory of the gases. And second one is deduce Boyle's law, Charles' law from kinetic gas equation. May ask Boyle's law or maybe ask Charles' law. Anyone comes, but not both at a time. So they may ask Boyle's law or they may ask Charles' law. Deduce the Boyle's law, either Charles' law from kinetic gas equation. And third one, most important one is state and explain Graham's law of diffusion. What is Graham's law of diffusion? And mathematical statement of Graham's law of diffusion. and numerical problems also important. And next one is a state and explain Dalton's law of partial pressure. This is also most important. And finally, derive ideal gas equation. Derive PV is equal to nRT. That is the ideal gas equation. So these are the most expected 4 marks questions in this chapter. Now come to very few. Now I'm going to give 3 more very short answer expected questions. My side I'm expecting this year. So first one is which of the gases diffuses faster among N2, O2 and CH4? Why? What is which of the gases diffuses faster among N2, O2 and CH4 and why? This is one more. And second one is what is Boltzman constant and give its value? What is Boltzman constant? Give its value. This is also one more important question. And last and final is calculate kinetic energy of 5 moles of nitrogen at 27 degrees Celsius. These are the expected 2 marks questions. But you read total chapter, go through the revision the total chapter, but these are the some important areas. What I want to say is these are the some important areas for exclusively for IP point of view. But entrance point of view or AEEE means JE mains or advanced purpose or in a NEET purpose, total chapter is important, but IP point of view, these are the most important expected questions. Okay, so with this we finish this lesson, students. Okay, thank you.
Thank you, Jahangir sir.
Thank you, madam.
Thank you very much for a very clear explanation regarding the states of matter. I sincerely appreciate your efforts for making this webinar a successful one, Jahangir sir.
Thank you.
So thank you. And dear children, in this session, we have learned about the gas laws. So please read the statements of all gas laws and try to learn that. And also you will get numericals along with these questions, like define Boyle's law, define Charles' law, and a numerical will be asked along with these questions. And also the most frequently asked 4 marks question is write the postulates of kinetic molecular theory of gases. And sir has given you all the questions at the end of the session in each and every session. If you go through the previous sessions also, you can find out the questions which will appear from those topics. Okay, I think everyone is writing down the notes and you are learning all these topics. So thank you everyone for giving us this great opportunity.
Thank you one and all. Thank you for giving me opportunity for one and all total webinar team principals. Thank you, madam.
Sir. Thank you so much.